Hello everyone, this is the Group 1 and we are going to talk about the BJT Small Signal Analysis Fixed Bias Configuration. So the topic for this presentation is assigned to the members as follows. For the Fixed Bias Configuration, it will be tackled by David Joshua Aniñon. For Small Signal Equivalent Model, it will be tackled by Charrise Mae Agnes. And for the working equation, it will be tackled by Kayle B. Atuel. For the theoretical values, it will be tackled by both Ryan Agnes and Juvannie Alquizar. And lastly, for simulating the circuit, it will be tackled by Humphrey, Kayle, Agnes.
Hi, I'm David Joshua. So now I will choose the fixed bias. So I'm gonna talk about what is fixed bias, fixed bias configuration. So first, I need to define it. And now, fixed biasing. Fixed bias. Biasing is the process of setting a transistor device DC operating voltage of a current condition to the correct level so that any input signal can be amplified correct by the transistor. Steady state of operation depends on a great deal in the base current collector. And voltage and collectors current for a transistor is therefore, if a transistor is operated as a linear amplifier, it must be properly biased to have a suitable operating point. Establishing the correct operating point requires the proper selections of bias resistors and load resistors to provide appropriate input current and collectors voltage condition. Just like that. Operating point is called the quiescent quiescent operating points, or just a Q point. So fixed biasing, this is the type of bias where base current is maintained constant for a given VCC by using a fixed resistor, so operating point must remain fixed. Using these two resistors and fixed current, initial operating point has to found just like this. Just like that. In a way, a fixed bias is the simplest DC bias configuration for a given transistor. So VB does not vary significantly during use, as a VCC is a fixed value on selections of RB. The base current IB is fixed. So therefore, this type is called the fixed bias type of circuit. And that's all.
Flashed on the screen is the small signal equivalent model. So the BJT collector-based emitter terminals contain for AC are equivalent to this. Visible on the left side, there's this resistance that's equivalent to beta RE. Then on the output side, equivalent to it is a current source pointing downwards with the value of beta IB, which is parallel to the output resistance RO. The aforementioned components are the scope of our BJT. Along with this, RB and RC are retained due to it being a fixed bias configuration.
Hi guys, my name is Kayle B. Atuel from CPE2A, and I'm going to present to you the working equation of RPIT. So let's get started. First is the parallel formula of RB and beta RE. It is just let's just simply multiply the RB and beta RE all over the sum of them. So next is the RE. This equation here is just a default equation, or default equation of RE, the 26 millivolts all over the IE. And next is the RO, is just a change of the VCE and the change of IC. Yeah. By the way, RO is just always given of the problem. So when you solve it, it is just it is already given. So here is the input impedance, and it's equal to the parallel of RB and beta RE. So Here, if RB is uh, greater than or equal to 10 times beta RE, input impedance will approximately equals to beta RE. So yeah, here in the output impedance, it is kind of similar to previous one, but it is just RC parallel to RO. If here the RO is greater than or equal to 10 times of RC, then the output impedance is equals to RC. So here, this is the AB is equals to negative RC all over RE. So that's all the working equation. Thank you.
Hi, I am Juvannie Alquizar, and I will be tackling a part of theoretical values, specifically the output and input impedance. This is our configuration, or the fixed bias configuration circuit. As you can see, we have a couple of 100 microfarad capacitor, and then a couple of different valued resistor, the base resistor and the collector resistor, and 18 volts VCC and an NPN BJT. To solve this circuit, we just have to transform it to an AC analysis. To do that, we have to short out these two capacitors, and it should look like this. To solve this circuit, we need to find the value of RE first, which have a formula of 26 millivolts all over IE. To find IE, we have to find IB first. So the formula for RB is equal to the VCC minus VBE all over RB, or the base resistance. All of this is equal to 18 volts, which is the VCC, minus 0.7 volts, 0.7 volts for the silicon base BJT, all over 550k ohms. And this should give us a value of 31.45 microamperes. And since we have already find the value of our IB, we can now go and find the value of our IE. So the formula for IE is a beta plus 1 IB. As you can see, if we go back to this part of the presentation, we have the value of beta equals to 100 and then RO of 60.75 k ohms. So 100 plus 1 equals to 101 times the value of IB, which is 31.45 microamperes. And this expression should give us the value of 3.2 milliamps. And since we already have the IE, we can now plug it in this formula. RE is equal to 26 millivolts all over 3.2 milliamps is equals to 8.125 ohms. Now, to find our input impedance, we just have to look back at our AC analysis. As you can see right here, to find the output impedance is quite simple. We just have to find the equivalent parallel resistance of these two components right here, the base resistance and the beta RE. So to do that, we just have to multiply 550k ohms times 100, which is the beta, times 8.125 ohms, which is the RE, all over 550k ohms plus 100 times 8.125 ohms. And this expression should give us an answer of 0.11k ohms. Now, going back or proceeding to the output impedance, to solve this part, it is actually similar to the input impedance. Actually, it is similar because we just have to find the parallel equivalent resistance of these two components, which is the RO and RC, or the collector resistance. So take note that if we have an infinite value RO right here, then our output impedance should approximately equal to the value of our RC. However, in this case, we have a value of our RO, then we just have to find the equivalent parallel resistance of these two components. To do that, you just have to multiply 4.7k ohms times 60.7k ohms all over 4.7k ohms plus 60.7k ohms, and this should give us the answer of 4.362 kilo ohms. So 4.362 kilo ohms is our output impedance, and 0.11k ohms is our input impedance. And that would be all. Thank you.
In the last video, Juvannie Alquizar solved the input and output impedance. Now, let us solve for the gain of the amplifier. First, the input impedance. In calculating this, we need to use the formula which is RB parallel to beta value RE in order to proceed. Let us first solve the beta value RE. 100 multiplied by 4.32 is equal to 0.432 kilo ohms. Now, let's proceed to the next step. 550 kilo ohms parallel to 0.432 kilo ohms is equal to 0.431 kilo ohms. Next is the output. The formula of the output is RO is parallel to RC. Just simply put down all the values and you can solve it. 60.7 kilo ohms parallel to 4.7 kilo ohms is equal to 4.36 kilo ohms. Now, lastly is the average gain. The formula for the average gain is negative RO parallel to RC divided by RE. Negative 4.36 kilo ohms divided by 4.32 ohms is equal to negative 558.71.
So simulating the circuit in Proteus. So this is the circuit for in finding the IB and IE. IB is supposedly 31.45 microamps, and IE being 3.177 milliamps. Now this is mine, so let's check here. 31.45 microamps and 3.2 milliamps. Let's check. 31.3 microamps, which is correct, and 3.16 or 3.2 milliamps. So that's correct. Now for the input impedance and output impedance. So this is the circuit right here. The small signal equivalent of the circuit, the BJT. The values will be 0.8172 kilo ohms and 4.36. 0.81 and 4.36, which is correct. ZI and ZO. ZI and ZO. So next is for the voltage gain. So this is the circuit and how to find the voltage gain. We have our signal generator and our oscilloscope over here. Our 18 volts battery. It's pretty much the implementation for the circuit. This one. Oops, for the circuit. Right, in Proteus. So after running the simulation, this is what will happen. We put the amplitude in 10 millivolts and our frequency in 1, and oops, it's a bit cut off, but our input voltage was 10 millivolts, and as you can see, I'm changing this knob over here. We get 5 in order for these For the channel A and channel B to be almost the same, we have to change this knob over here. As you can see, it's 5.71 volts, and this is 10 millivolts. We run the simulation, one shot. It's also correct because it's the opposite of the input sine wave. As you can see, channel A is input and channel B is output. And if we calculate the ratio between the two voltages from input and output, it's 5.71 volts divided by 10 millivolts. We got negative, we get negative 5.71. Almost the same. My answer in here is negative 574.29. So as you can see, it's not the same as in the theoretical, which is negative 574.29, but it is close. As you can see, it's 5.71, and we already did the calculation. We're done with the voltage gain, or the ratio between the voltage of the input and the output. We're done with this, and then that's all. We've proven our theoretical value through the use of Proteus. And that's all. Thanks for watching.
And that concludes our presentation. Thank you for watching.